thanks a lot. Thanks a lot to the organizers for inviting me and talk about DarkSUSY and what you can do with DarkSUSY in terms of indirect detection. So, I mean, just to start with a sort of general overview of what DarkSUSY can do, what we really want to do is to calculate various dark matter rates, dark matter signals, and of course we want to do so in a consistent way. And the typical flowchart of what you want to do is you want to provide some particle physics parameters, so essentially define your model. You want to use that to calculate masses and couplings, check for obvious constraints, whether the model is still viable. And then you want to check, because it's a dark matter model, that you actually get the correct relic density. And you want to calculate rates, in particular direct and indirect detection rates, which I will be talking about today, but also, I mean, dark matter could be self-interacting, for example. And then in the end, you want to compare with data. Yeah, so in principle, DarkSUSY is designed to, in principle, be able to do all these steps. The clear focus is, however, on these two parts here. So on precision calculations of the relic density, both for freeze-in, for freeze-out and more complicated freeze-out scenarios, and there are various rate calculators for direct and indirect detection rates, all self-interactions. Yeah, and then there is support to do this part as well, based heavily on external code. And then finally, for a comparison with data, so then you need to look at actual experimental data. You need to implement likelihoods. So this is not the part of DarkSUSY. DarkSUSY just predicts the rate. And then you need tools for global fits, like, for example, Gambit. Okay, so technically, DarkSUSY is a large library of subroutines and functions that you can use to calculate these dark matter observables. Yeah, so given the constraints by the programming language Fortran that we've used, we've tried to make the code as flexible and modular as possible, and I think it works pretty well. And then, of course, the advantage of Fortran is that it's really fast. And as you will see, once you start playing around a bit with this, and I give you some instructions here, it is really simple to use. So another important aspect is that DarkSUSY is really not linked to supersymmetry anymore. Yeah, since version 6, it has been, you can call it unSUSYfied. And there's, I mean, a couple of particle physics modules that are implemented, including, of course, the MSSM. That's how DarkSUSY started with. So very quickly, the main structure of the code is such that you always have, as a user, to provide your main program, and we provide various examples of that. And then you link to the main library, the core library, that contains all the particle physics independent stuff, and one of the particle physics modules. So technically, the particle physics modules are defined by a small set, a handful, essentially, of interface functions that essentially define what the particle physics module can do. So this is the only thing that the DarkSUSY library, the core library, needs to know about the particle physics module, and that is also the only thing that you, as a user, need to provide if you want to supply a new particle physics module. Yeah, for example, I mean, you can only provide, for example, the invariant annihilation rate for indirect searches and the relic density for a new model. It can even be tabulated, and then you can use the full functionality of DarkSUSY to access this. There's also the concept of replaceable function. This is a bit more technical, so you can ask me about this later. So just to mention a few physics highlights, what you can do. So as I mentioned, I mean, one of the focus points of DarkSUSY is really to provide accurate relic density routines. And some recent updates include, in particular, the support for freeze-out calculations in secluded dark sectors. So taking into account an arbitrary evolution of the dark sector temperature with respect to the photon temperature. Yeah, so a typical situation is that you have like the two sectors in thermal equilibrium at very early times, then they decouple, and entropy is conserved separately in these two sectors. So that means that this function here, the ratio of the two temperatures, is just a function of how the dark and visible sector degrees of freedom evolve. Yeah, and this is all fully implemented and in a consistent way. Yeah, and then there's also support for coupled Boltzmann equations that you need to use once you go beyond the standard assumption that during freeze out, your dark matter particles are in kinetic equilibrium. And then there are various other things. You can calculate late kinetic decoupling, the resulting cutoff in the power spectrum. various indirect detection routines or rates that I will mention, dark matter self-interactions, and also related to the indirect detection routines, there are radiative corrections implemented. So of course, this is model dependent. So in the MSSM for neutralino dark matter, we have included the leading corrections from internal bremsstrahlung from both U1, electroweak, and strong interactions. Okay, and then sort of as a really new addition, only since yesterday, we put yesterday this work here on the archive. DarkSUSY also allows for freeze-in calculations. So just because it's new, I have to mention it here. So this is an example for a very simple application, the scalar singlet model. And then you see that there's basically, so, okay, in this model, dark matter is a scalar, a real scalars, not charged under any of the standard model gauge groups, so a singlet. And then, of course, there's exactly one dimension 4 operator, how you can couple it to the standard model, the Higgs portal. And then basically you have two different situations. Before electroweak symmetry breaking, it's just this 4-point function, 4-point coupling, and after electroweak symmetry breaking, scalar annihilation or production of the dark matter particles, if you view it in the other direction, dominantly proceeds through this Higgs resonance. And here you see the value of the coupling that is needed in order to get the radiative density, and you see separately the effect when you include quantum statistics in the standard model particles, so because you produce in the relativistic dark matter and the relativistic regime, you're actually sensitive to going beyond the Maxwell-Boltzmann assumptions, but also other thermal effects. So we have included here thermal masses for the standard model particles and thermal masses induced by the electroweak phase transition, as noted by these two figures, but also the QCD phase transition. So and you see that both effects are about equally important. Now, if we go to very low reheating temperatures, such that we essentially are always in this regime, but can contract this interaction to a point-like interaction, then the relevant interaction is essentially a dimension 5 operator, meaning that the freeze-in production becomes UV dominated, and therefore dependent on the reheating temperature. And that means that if you go to very small reheating temperatures, you can actually reach a situation where the couplings that are needed in order to get the right radiative density are so large that they are in principle testable at colliders. So here is the current limit from the invisible decay of the Higgs. Okay, so this is just one example of the things you can do with DarkSUSY. Other examples you are sort of made explicit in this directory here when you download the code, and also on the web page there are a few explicit examples always explained and then with a code example. So this is a very good starting point to explore what you can do with the code. Okay, so then let's move on to indirect dark matter searches. And this is something that Michele already talked about earlier today. And of course, I'm very grateful for the nice overview, because there's a lot of things that I don't have to repeat now. So the idea is basically that you look for places in the halo or in the cosmos where the dark matter densities are high, because then the rates for dark matter annihilation into some standard model particles would be high. And you would try to spot these particles here in cosmic ray spectra or gamma ray spectra of various kinds. And DarkSUSY has routines to provide rates for all these final states. So then it's important to notice that these are conceptually quite different. So you're basically probing different parts of the halo. So this is a sketch of the dark matter halo. This is the center of the galaxy with our with a bulge, and then the disk, and this is the location of our sun. So positrons, they lose energy rather efficiently. So you only ever probe a relatively small region in the local neighborhood. With antiprotons, you can probe a much larger part of the halo. And with gamma rays, they propagate essentially unperturbed. So you probe essentially a small cone or a line of sight. And this is something that is very nice about gamma rays, because they basically probe the dark matter distribution directly, as opposed to charged cosmic rays, which of course diffuse and are deflected by magnetic fields. So you need to know a lot more or be much more certain about your modeling of the cosmic ray transport in these cases than for gamma rays. Okay, so this is also something that Michele has already talked about. So for the gamma ray flux in particular, in most situations, you have a nice factorization of the expression for the flux. Yeah, so one is just a line of sight integral of the number density or the energy density squared of the dark matter. So this is something that could in principle be observed. And from the point of view of the signal, this provides essentially, well, some angular information if you have a profile that is not extremely cuspy, but most of all, an overall normalization of the signal. Yeah, and since, in particular in the inner parts, as also discussed by Michele, the dark matter density distribution is not very well constrained, there's a significant uncertainty related to that. On the other hand, there's this particle physics factor. So here there are only particle physics quantities entering. So once you have your particle physics model, in principle, you can calculate this to high accuracy. And then, of course, especially when you have spectral signatures to look for, this can be used as a smoking gun to identify a dark matter signal. Okay, so let's first talk about this first part, the normalization of the signal. So these are J, or for decaying dark matter, D factors. Yeah, so if you go to this, like after having downloaded the code, if you go to this folder here, you can just list a lot of all these example programs, and they are sort of dedicated like minimal examples. And in particular, there's this example here that demonstrates how to use the line of sight integration routines in DarkSUSY. So there are various options. There's some heel-pix support for heel-pix integration. There are dedicated routines that allow you to calculate very cuspy profiles where the heel-pix integration does not give very accurate or not very robust results. And this is something that was used, for example, in the recent CTA consortium publication about the sensitivity forecast of CTA to a dark matter signal from the galactic center that Michele also mentioned. Then this is a plot that you've seen as well. You have to ask what kind of annihilation spectra are we looking for, and then there are the secondary production. So you have dark matter particles annihilating to standard model particles that then hadronize and decay and give sort of a large number of photons, a significant photon flux. However, this flux here is rather featureless. Yeah, so you can use it in a very efficient way to constrain a dark matter signal, but if it is subdominant, it is hard to really discriminate it from astrophysical backgrounds. On the other hand, if you have an annihilation channel where you have a photon in the final state, then this typically leads to very pronounced spectral features close to the kinematic endpoint that corresponds to a photon energy equaling the dark matter mass. So this is, of course, suppressed. Dark matter is neutral, so it has to be suppressed by powers of the electromagnetic coupling constant. But since the spectral feature is so pronounced, this kind of channel has a very nice discovery potential for dark matter. Okay, so for the particle or for the model independent part, we have sort of per default, we have tabulated a large number of Pythia rounds, interpolate between these such that you can directly access them for all possible standard model final states. But we've also tabulated alternative spectra, including, for example, different treatments of QCD uncertainties. And there's a very simple way of how you can switch between these dipoles, and this is demonstrated in one of the example programs. So just one example of where this was used in practice is again this CTA consortium publication, and these spectra entered the final limits or the sensitivity predicted for CTA. And as Michele also stressed, you can see here that CTA has really a very nice prospects of probing TeV scale wind dark matter. Okay, so then in the remaining 5 minutes or so of my talk, I want to address what happens when we include radiative corrections. So of course, at tree level, dark matter can typically annihilate into standard model final states. I call them just F. And then at next order in perturbation theory, if these particles are charged, there are inevitably these processes where you emit an additional photon in the final state. As opposed to the case where you have two photons, direct annihilation to two photons, which is suppressed by two orders of the electromagnetic coupling constant. So then you can sort of, in a general way, discuss the different features of these kind of diagrams that you can have. And if we really have a point-like interaction here, yeah, then in many cases, these diagrams will dominate, yeah, and you can do these statements also in a gauge invariant way, because of course you can't look at individual diagrams in a naive way. Yeah, and then the point is that these final state photons here will dominantly be emitted in a collinear way, and that leads to a model independent spectrum that only depends on the center of mass energy and the mass ratio, or the ratio of the center of mass energy and the final state mass. On the other hand, there are two types of interesting situations where this kind of process can dominate over the model independent part. And this happens either if the final states are bosonic and there's a T-channel particle that is degenerate in mass with the final state, with the dark matter particle, or in the situation where the two-body annihilation is for some reason suppressed by some symmetry, and this symmetry suppression is lifted once you add an additional photon. Yeah, this doesn't work in this case because, as I said, you have dominantly collinear emission of the photon, which means that the quantum states of this virtual final state are the same as this one. Okay, so for the MSSM, of course, this is particularly relevant because neutralinos, the annihilation of neutralinos into fermion final states is helicity suppressed, and then you can emit an additional photon, lifting the helicity suppression and giving rise to very nice spectral signatures. Yeah, so what we've implemented in DarkSUSY is there are the full NLO expressions for these kind of processes, including all diagrams and the full mass dependence. So for gluons, we have in principle the same thing. Yeah, so in a sense, it's a trivial relation to the photon case. But there the problem is that if you have a quark-quark gluon final state and just a quark-quark final state, we don't observe the gluons directly as in the case of photons. Yeah, so in the end, we still have to sort of use Pythia to hadronize these final states and then look at the resulting spectra. That means that we can't disentangle the three-body and the two-body final states in the same way, meaning that we should also, for consistency, take into account the loop contributions, the loop corrections to the two-body final states. And of course, it's very expensive to run Pythia for each individual model point. So the solution that we opted for in DarkSUSY is to basically map the full MSSM parameter space to a simplified model in the limit of 0 relative velocity of the incoming neutralino pair. It's the same kinematics and global quantum numbers as for decaying pseudoscalar, and then add this dominant sort of mistake that you would do by doing so, namely from this virtual internal bremsstrahlung, essentially by hand, making sure that gauge invariance is respected, of course. And for the second part, we noticed that the spectra that you get, I mean, this is a case for antiprotons, but the same would hold for photons, for gamma rays, is indeed not so different for just two-body final state and three-body final states in these extreme cases, where either this one dominates or this one dominates. So the total spectrum can be approximated to very good accuracy by a linear interpolation between the two, depending on how strong these contributions are for a given parameter point. Okay, so for electroweak corrections, you can do the same game, but there are conceptual differences. Yeah, and while one is similar to the case of gluons, so if you emit a massive gauge boson here, it will decay and fragment and give sort of an additional contribution to stable final particles at lower energies typically. But what is nice is that, of course, you open up new channels. Yeah? So even if you, for example, have a completely leptophilic or neutrinophilic dark matter candidate annihilating at tree level only into neutrinos, taking into account these channels will even give you an antiproton flux. Now, if you want to do this in implementing all the contributions in a given model, like the MSSM, and this is done in DarkSUSY, of course, you see, I mean, already by eye that this is way more complicated, but it's also worth it because there are significant new effects that enter that you simply cannot capture by just following the simplified prescription. So one of the things that I want to stress are, for example, spectral signatures that you even get for the positron and neutrino signals. So just to illustrate this, this is an example for the photon spectrum, where this is the contribution that you would have just from tree level, just looking at two-body final states, adding, I mean, this is the contribution from SU2, and this is the spectral signature that you get from virtual internal bremsstrahlung photons. And then and this is my last slide, and for SU2 corrections, you see significant enhancements also for the other spectra. So for example, if you look at the Xeon line, the dashed one here is the tree level contribution, and you have a very pronounced spectral signature taking into account electroweak corrections. Okay, so my take-home message is, well, 2 points essentially. So one is you should just keep in mind, I mean, in many cases, these model-independent implementations of radiative corrections, SU2 corrections in particular, work very well. There's no reason to doubt them, but not in all cases. So you should think twice at least. And the other take home is that, well, it's really easy to get started with DarkSUSY. So just go ahead and have a look at the examples and try them out. Thanks for listening.